Hi everyone, I'm Angela from the Central Bank of Armenia. Welcome back to our YouTube channel. We're starting off this series of videos called Space Shuttle, Free Ticket to Secure Open Source Software, where each week we will be talking about some specific topics, models, and show their applications in one of the most powerful and secure open source softwares called Julia. And all of the training materials will be made available as a user guide called the Space Shuttle, which you can use together with these videos. And one more thing, this user guide will include not only Dynare Julia, but also Rise and our Python applications. In this particular video, we're going to learn how to download and install Julia, as well as how to incorporate Dynare in Julia, and of course, how to run a simple three-equation model developed by Douglas Luxton for training purposes only. So before we start, we would like to thank the Dynare Julia team, in particular Michel Juillard, for his immense contribution to Dynare and Julia. And if you want to learn about the history behind the development of these programs, as well as the future evolution, you can take a look at the video recording of Michel from a Better Policy Project seminar, and the link is in the description below. So let's start by looking at how to install Julia. To install Julia, you simply need to go to this page, julialang.org, and download the latest Julia version compatible with your computer. And after you have finished downloading the program, just run it by following the directions. So to incorporate Dynare in Julia, you can check out the GitHub page where you can find very helpful materials for beginners. So now let's take a look at our illustrative model with three equations. So our illustrative model is a linear rational expectations dynamic stochastic general equilibrium model. So the idea is to understand implications of a simple model first, and then extend it with different features, for example, open economy and so on. So our model is dynamic because it incorporates leads and lags of the variables. It's stochastic because it is exposed to different shocks, and we're thinking about it as a general equilibrium system where the variables are interacting together. So the first line of the code, as you can see on the screen, includes the description of our endogenous and exogenous variables. You can use the command var in Dynare to define endogenous variables. So in our model, we have three endogenous variables: inflation, interest rates, and output gap. So of course, don't forget to use semicolon every time you're done with a specific command. So on the other hand, you can see that our exogenous variables include shocks to inflation, interest rates, and output gap. So in our model, every endogenous variable needs to be defined with an equation. So here, by using the command model, we can go and open a workspace for defining each endogenous variable. So you can see that in our model, inflation is defined as a function of its forward and backward-looking components, output gap, and a shock, where the output gap is defined by a function of its lead, lag, interest rates, and the shock. Of course, in our model, we are defining real interest rates as the difference between nominal interest rates and inflation. And last but not least, we have monetary policy reaction function, which is a function of the deviations of inflation from its target, output gap, and the shock. To finish the description of our endogenous variables, you need to write and command and semicolon, of course. So you can add initial values for endogenous variables with initval command. In this specific example, the initial values for endogenous variables are the steady state values, but you can use different values for your specific economy. So the steady command is used for calculating steady state values of the variables. So what we do here is that we take all the leads and lags out of the equations and define that as another model. And by solving that last model, it computes the steady state values for our variables. So the check command does the eigenvalue analysis of our model, and after that, we need to define distributions for the stochastic processes or the shocks. And here in our model, we assume that the shocks are Gaussian processes. So we write this assumption of linearity with first order equal to 1, which means that we're taking a first order local approximation. But of course, our model is linear. But if the model was nonlinear, this would linearize the model by simply taking a first order approximation. So to incorporate Dynare in Julia, you simply need to type this code in Julia using pkg at Dynare. And thereafter, you need to prepare your model in Dynare and make sure that your model has .mod extension, the file that you're going to upload in Julia. And by having your file, we can already go to Julia and run our code. So here I have already ran the code for our simple model. You can see that in order to add our file that includes our model, I am simply typing this code, context equal to Dynare and the path of my file, and simply running the code. So by running the code, you can already see we're getting the main results of our model, the main output. And in order to see the impulse response graphs, you can go to the folder where you have saved your .mod file, and there you can see an additional folder. If you open that folder and once again you click on the graphs folder, you can already see the impulse responses to different shocks. Here we have impulse responses to inflation shock, to interest rate shock, and output gap shock. So let's go back to Julia and our main output of the model. First of all, we have the steady state values for our endogenous variables. We have the reduced form representation of our model, which for each endogenous variable is a function of the state variables or backward-looking components of inflation and the lag of output gap and a shock in the model. You can also see the descriptive analysis of our main variables, also correlation metrics, autocorrelation coefficients. Here, I would like you to pay attention to the autocorrelation coefficients. To provide an illustrative example, the autocorrelation function for inflation is correlated with its first lag by 0.5, with its second lag by 0.2, with its third lag by 0.5 and 0.1, and no correlations behind that. So this means that our economy has very low inflation persistence and persistence to any of these variables. So in our upcoming videos, we're going to elaborate more on Dynare-Julia applications, semi-structural models, reduced form representations of the models. So make sure you're following our YouTube channel for more, and thank you guys for your attention. Bye.